Lab 1, Constant Velocity Motion. The purpose of this lab is to describe the motion of an object moving at a constant velocity using Newton's second law. To do this, first I use a video camera to record a real-life object moving at a constant velocity. Using Tracker, I take measurements of the object's position with relation to time. I use the initial conditions from the data gathered to construct a model using Newton's second law that should describe the object's motion. Finally, I compare the predicted motion of the model to the motion of the real-life object. This allows me to determine if I was able to successfully describe the motion of the object using Newton's second law. For this experiment, I have chosen to observe a tennis ball rolling across a flat surface. I'm going to use Tracker to measure the position of the ball versus time. First, I calibrate the video by placing the calibration stick against an object with known length. I've decided to use the tennis ball itself, which has a diameter of 6.7 centimeters. Next, I set up the coordinate axes. The camera was slightly tilted while taking the video, so I compensate for that by rotating the x-axis until it is parallel to the surface that the ball rolls on. Then I select the portion of the video where the ball appears to be traveling at a constant velocity. I've chosen frames 42 to 76. Now I can begin taking measurements by marking the center of mass of the ball from frame to frame. On the right, I can see the data gathered in graph and table form. I will come back to this later, but for now I only need to take note of the first two sets of values because I will be using them in the next part of the experiment, where I will set up a model using Newton's second law, which will predict the motion of the ball. Newton's second law states that change in velocity over change in time is equal to the net forces acting on the ball over the mass of the ball. Delta V over delta T equals F net over m. With some algebraic manipulation, this can be written as V sub f equals V sub I plus F net over m delta t. Since this is a model of an object moving at a constant velocity, V sub f equals V sub I, which means that this term, F net over m delta t, must equal 0. Since I know that m is not equal to 0 and delta t is not equal to 0, it follows that F net must equal 0. Now I need to determine V sub I, the initial velocity of the ball. Using the first two sets of values from Tracker, I determined that initial velocity is 0.788 meters per second. I set up the model by entering the relevant values into a Python program that predicts motion using Newton's second law. Here are the key changes I made to the program. The mass of the ball is 5.8 grams, or 0.0058 kilograms. This value will be cancelled out in the equation, but I entered it for the sake of completeness. The initial position of the ball is 0, Its initial velocity is 0.78800. I've set delta t to 0.01. The program will predict the ball's velocity for 1.2 seconds, which is approximately the same length of time as the video clip. As discussed before, F net is equal to 0. When I run the program, you can see the ball's motion in the first window and a graph of the ball's position versus time in the second window. The last part of the experiment is to compare the predicted motion of the model to the motion of the real-life object. I enter the values from Tracker and the values generated by the Python program into a spreadsheet and create a chart to compare the two sets of values. They are fairly close, but the model data has a constant slope of 0.788, while the experimental data has a slightly smaller slope and seems to be a little bit curved. How can I account for these differences? What does it mean? When I set up the model, I assumed that the ball was traveling at a constant velocity, and so I set F net equal to 0. However, in the real world, F net is not equal to 0. There are forces acting on the ball that are causing it to slow down. This explains the lower slope of the experimental data, as well as a downward curve which indicates decreasing velocity. What happens if I flip the coordinate axes so that the positive x-axis is pointing towards the left? The key thing to remember is that the motion of the ball remains the same. It is the way that the motion is described that changes. Here is the same video opened in Tracker, but this time I've set the coordinate axes so that the positive x direction is to the left. Notice that the values for x are increasingly negative and the graph is a negative slope. However, the ball's motion is unchanged. In conclusion, I was fairly successful in predicting the motion of the ball by using Newton's second law and assuming that the ball was traveling at a constant velocity. However, this assumption causes us to set F net equal to 0, which means we disregard the forces that are acting on the ball. It is evident from the experimental data that the final velocity of the ball was not equal to the initial velocity of the ball. Therefore, the ball was not traveling at a constant velocity, and F net was not equal to 0. I would be better able to model the motion of the ball if I were able to determine all of the forces acting upon it.